All right, so the exams, the average was about 85%. If you have any questions about how it was graded, or you think you should get more points, or if you think you should get less points, come talk to me in the next. That never happens. It's like so statistically incredible the way it works out. It's like the only people who come talk to me think they should get more points.
My brother did it the other way once.
Did he?
Yeah, the guy didn't give him a point off. He said, "You're the person that ever had to do that."
Yeah, right. Yeah, sometimes two people will come and say like, "Well, we did the same thing, and he got," and then I'll be like, "Okay, give me the other person's test. I'll fix it." Okay, but come talk to me in the next few days, maybe the next week or something. I don't. If you have a problem with it, I don't want to talk about it at the end of the semester because 1 point makes a difference in your grade or whatever. If you see a problem, come talk to me soon about it. And then one thing that I saw, I mean, for the most part, people understood what was going on. There were a lot of problems where I asked for a unit vector and people didn't normalize it. They didn't give a unit vector. They just gave the vector of whatever length it was. That was probably the most common mistake. One simple mistake that I saw a lot that I'd like you to keep in mind is for vector variables, use vector symbols to indicate that they're vector variables. So if you have a variable f and it's a vector, just give it the little arrow over the top. Okay? A lot of people left that stuff off. I didn't take off points for that, but please do that. Anybody have any questions about the test, or were there any problems that you'd like to see me do? I don't want to go through the whole thing, but I'd be happy to go through 1 or 2 problems.
Could you do 8?
8?
Yeah.
Yeah, sure. Okay, so it looked like this. So you had 2 boxes, each on a separate incline. And they're connected to a cable that goes over a pulley. This one has a mass of 15 kilograms. This one has a mass of 10 kilograms. And then there's a downward force of 100 newtons here and a horizontal force of 50 newtons here. And you had to draw the free body diagrams. So first for the 15 kilogram box, there was the weight, so a force of 15 G down. There was the 50 Newton force this way. There was the cable tension this way, so I'll call that T. And then it was a friction contact. Hi. Thanks. friction contact with the incline. So whatever, let's say we're using this coordinate system for both of them. Then the way you represent that is just as a full unknown force vector. I'll call that the force on the 15 by the ground. Vector symbol because it's a vector variable. And then for the 10 kilogram box, you have the weight, so that's 10 times G. Then you have the downward force of 100 newtons acting there. You have the cable tension acting that way. And at the ground, you have the force on the 10 by the ground. And that's it. Any questions about that? Yep.
I guess I have a question about the direction of the friction.
Yeah.
Is that always just going to be in the direction of the coordinate system? Or
Yeah, so to us in this class, contact with friction is always just an unknown force vector. So we're not breaking it up into a normal force and a friction force. We just draw it as an unknown force vector.
Okay.
So it doesn't matter. The direction of these axes depend on the directions of the coordinate axes. They don't depend on the direction of the incline.
Oh, okay. Gotcha.
Okay.
Thank you.
Any other questions about this one?
I had a question.
Mm-hmm.
If there is no friction as a 10 gram, and do I need to draw the reaction force for 100 Newton?
If there was no friction?
Do I need to draw the reaction force, one reaction force for 100 Newton?
Yeah. If there was no friction, it would look like this. You have the weight of 15G. You have the horizontal 50 Newton force. You have the cable tension. And then contact without friction is a force vector with a known direction, and the direction is perpendicular to the surface of contact toward the chosen body. So it's the normal force.
What about the 10 gram?
And then for the 10, you have the weight, the downward force of 100, the cable tension, and a normal force perpendicular to that surface.
But normal force is only for the reaction force of the gravitational force. Whereas you have the 100 external force pressing down. Do I need to draw the random reaction force for just 100 Newton?
Nope. This, so
Because theoretically, if you press down stuff in, this 100 Newton could be added up to the normal force. That's what I see.
right. But say that this is in equilibrium, okay? If you calculate what this normal force has to be for this to be in equilibrium, with this at 100, you get one value. If you change this to 500, you get a different value for that reaction force. So that reaction force, it does depend on that, how big that force is pushing down. It does change. But you don't change the name. The way that you need to think about it is just, you look at that contact and you think, okay, what kind of contact is it? If it's a pushing contact without friction, a contact without friction, then you think that force is perpendicular to the surface of contact, and it's toward the chosen body, and then you write the scalar variable associated with it. So you always treat it the same. The numerical value it takes is going to depend on the other stuff going on. Okay? Yep. So it's really just sort of a systematic approach. You look for the type of contact. You treat that joint the same every time, and then you go into Newton's laws and calculate what the values are. Any other questions?
Could you go over 3?
Yep. Okay, so number 3 says, what two unit vectors are perpendicular to the vector A, B, and the vector CD? The way we're going to do that is with the cross product. So we'll call it AB0 and cross it with CD0. And if you take that cross product, you get 0, 0, and then for the Z component, you get AD minus BC. So in other words, a vector that's perpendicular to both of these is this. The unit vector, and you could go through the whole process of calculating the unit vector based on these components. But what you can see from this is that this vector only has a non-zero component in the z direction. And so you know that the unit vector in that direction is just going to be equal to either 0, 0, 1 or 0, 0, negative 1. Because those are the two vectors with a length of 1 that are in the same direction as this. Or that are in the same direction as this and the opposite of this. You could go through the process of doing this calculation and divide by the, make it a unit vector by dividing by the square root of the sum of the squares. You'll get the same thing. Any questions about that one? Here's what's going on in this problem. So if this is the there's the x-axis, there's the y-axis, okay? And we have two vectors that live in that plane, because they only have x and y components. So let's say one of these vectors is this, and one is this. The two vectors that are perpendicular to these two red vectors are the two vectors, the two directions going out of that plane. So this and this. The unit vectors in those two directions are 0, 0, 1 going up and 0, 0, negative 1 going down.
I understand that. Let me say way more this. So why do you choose 1 and negative 1 though over anything else? Are those just going to be the standard of what you're going to do?
Instead of 0, 0, 2 and 0, 0, 3? Because I asked for unit vectors. And these are the two vectors in those directions that have a length of 1.
Oh, I see. So that's okay.
So depending on like what A, B, C, and D are, this could be 14, And so this perpendicular vector would be 0, 0, 14. But then when you went through the process of calculating a unit vector in that direction, you'd get 0, 0, 1.
So I stopped at that one.
Okay. Yep. Any other questions about that one?
No, but
Okay.
part B for number 2, when we were given a magnitude, solving for the unit vector?
So number 2, you come up with, so you calculate these 2 unit vectors. For A, you calculate u and negative u. And then to find 2 vectors in those directions with a magnitude of 50, you do 50u and negative 50u. And you can test that too. Like if you ever forget that, or you're not sure what to do, try dividing by 50, try multiplying by 50, and then use the formula to calculate the length of that vector, and you'll see that this one has a length of 50 and the other one has a length of 1/50th. Any other questions?
Could you briefly go through 6?
6. I am going to end up doing all these, aren't I? Okay, so 6. The force vector, okay, so we have one thing there, one thing here. This is A, this is B. And it asks, what's the force vector applied to A by the cable? So the cable tension is equal to 100 newtons. What's the force vector on A by the cable? The cable always applies a force away from the chosen body, so we know that it's going to be in this direction. Well, we know that magnitude is 100. So we're trying to figure out this vector. So the way to do that, the vector that's in the proper direction is going to be equal to the coordinates of B minus the coordinates of A. So that's 9.4, negative 3.42, minus, yikes, minus the coordinates for A, which are negative 4.70, positive 1.71. And you get a value of 14.1, negative 5.13. Then the length of that vector, the magnitude, is 14.1 squared plus 5.13 squared, square root. The unit vector in that direction is equal to 1 over the length times the vector. And then the force on A by the cable is just equal to 100 times that unit vector. Any other questions? Okay. So the next topic that we have to go through is how to deal with joints in 2 dimensions. And this is a really big topic in this class, a really important one. 2D joints. A joint is a connection between bodies. Each joint applies a specific type of loads to the connected bodies. And so I'm just going to go through all the joints that you're going to have to deal with in 2D, organized into how many variables they introduce into the problem, and what type of loads, how you have to treat these as loads. So the category 1. So joint category 1. So these are joints that apply, okay, they introduce one variable into, let's say, into the free body diagram of the body. And they apply a force vector to each body with a known direction. So the first one is, in this category, the first one is contact without friction, and we've already talked about that one. So let's think of that as think of that as a ground and a body in contact with it, but there's no friction at that contact. I'll call this body 1 and this body 2. And I'm going to draw free body diagrams of both of these. So free body diagram of 1. I'm not going to worry about any of the other stuff that might be going on with this. I'm just going to draw the part of the free body diagram that deals with that frictionless contact. But body 1 has a force acting like this. I'll call it R. You can call it whatever. It's a force vector in a known direction, and that known direction is perpendicular to the surface of contact toward the chosen body. And then the free body diagram of body 2. So that's the ground in this case. I'll separate out like a chunk of the ground. That joint, one way to think of it is this R is the force applied to body 1 by body 2. So over here you're going to have an equal and opposite force because of Newton's third law. The other way to think of it is this is a frictionless contact, so you have a force that's perpendicular to the surface of contact acting toward the chosen body. And in this case, the chosen body is the chunk of the ground. So that force vector is going to be that way with a value of R. Those have to be the same. Any questions about that one?
They're both, so the both R's are perpendicular to the body.
They're both perpendicular to this surface.
Okay, gotcha.
Nope, because what that negative would be doing is changing the direction, and we're doing that with the arrow. So you could keep the arrow the same and make it a negative r, but that's not how we're doing it. But what you can't do, so you could change the r to a negative r, or you could change the arrow, but if you do both, you get a double negative thing, and it's actually wrong then. So don't think of that as like the deluxe model of Newton's third law, you know what I mean? So one thing to notice about this is for this kind of joint, R can only be positive because you can't ever have these, if it's a frictionless contact, you can't ever have the ground pulling down on member 1. Okay, so R must be positive. If you ever do a calculation and you calculate an R that's negative, something went wrong in your calculation or something in the problem design, the structure that you're designing isn't going to work the way you mean it to.
To what extent can we use statics to solve real-life problems, like when you're designing something? I know that for sure that you're supposed to use finite elements if you want to be precise about the reasons.
Yeah, well, statics, I mean, you can, everything that we're talking about in statics, you can use all the time. We're not going to make any of the, so you're talking about in D form, if you're trying to do realistic stress and strain calculations, in many cases you have to use a numerical approach because we had so many simplifying assumptions that we used. They're not going to work for this kind of body or this shape or this kind of material, remember all that stuff? There's nothing like that in statics. So everything we're talking about works perfectly.
So can you consider statics as like more like a way to calculate the distribution of the load, per se?
Well, the topics that we're doing right now are just for calculating the external loads on objects. And then remember, in D form, you use those external loads to calculate the stresses. So you could think of this as like the first step in getting to the stuff that you get to in D form. Okay, so we're in this first category, all joints that introduce one variable into the free body diagram. And here you see how that variable occurs. In these two free body diagrams, the variable is R. And it does it by applying a force vector in a known direction. So here's the second type of joint in that category, a roller. And you see these in problems a couple different ways. Sometimes you see it just as like a little wheel or something between two bodies. Sometimes you see it as one of the bodies wearing sort of like a roller skate. That's my favorite kind, because roller skating's so fun. Okay, but those mean the same thing mathematically. So the free body diagrams, if we call this body 1 and this body 2, or this body 1 and this body 2, the free body diagram of body 1 again, you can think of it as basically exactly the same as contact without friction. You just have a force that's perpendicular to the surface of contact, and the force is going toward the chosen body. So that and a single scalar variable r. And if you isolate the other body, so isolate a chunk of the ground, you have an equal and opposite force like this. And again, notice that that roller can't pull the objects together. It can only push them apart. So, again, R must be positive. And then the last one in this category is a pin and slot joint. So let's call this member 1, and there's a pin connecting member 1 to a slot in member 2, so that pin can slide along this slot. And this is member 2. And so this produces a force vector perpendicular to the slot. So free body diagram of member 1. Is like that. And a free body diagram of member 2 is like that. So again, this is going to be the case in all of these. These forces are equal and opposite because of Newton's third law. And notice in this one's different than the other two. This slot can, this connection between 1 and 2 can push member 1 towards the left, or it can push it towards the right. Bless you. So the variable R can be positive or negative in this case. It could only be positive in the other two cases. Any questions about any of those yet? In the free body diagram, you could. Yeah, it's either way is fine. Okay, so now category 2. Joint category 2. So the joints in this category introduce two variables into the free body diagram. And they apply a fully unknown force vector to each body. Okay, so joint number in this category, joint number 1 is a pin joint. and it looks something like this. You can think of that as like a hinge. If this is member 1 and this is member 2, then a free body diagram for member 1. Looks like this, the force on 1 by 2. And the free body diagram, that's member 1. The free body diagram for member 2 has a fully unknown force vector that's equal to the force on 2 by 1, and that's the same thing as negative F12 by Newton's third law. And the second one in this category is contact with friction. We've already talked about this one. This looks something like this. It really looks the same as contact without friction, except something in the text will just tell you that there's friction at that contact. So here's member 1, here's member 2. A free body diagram of member 1. Looks like this, the force on 1 by 2. And a free body diagram of member 2. Isolate a little chunk of the ground. Looks like force vector F on 2 by 1, and that's equal to negative F12. And then the last category only has one type of joint in it. So joint category 3. How many variables is this one going to introduce? The last one introduced 2, so this is going to introduce 3. And this applies a full force vector and a couple to each body. There's only one of these. It's called a fixed joint or a weld joint. It looks like, sometimes you see it like this. Sometimes you see it drawn like there's a little notch in one of the members like this. But they mean the same thing. That's a connection that just doesn't allow any motion between these two bodies. I'll call this member 1 and this member 2. So a free body diagram of member 1 looks like this. You have a full force vector. I'll call that the force on 1 by 2. And then you have a couple, which I'll represent as a pure moment. And for couples, we can use that subscript notation because couples are made up of force vectors. So as long as you always use the sign convention where a positive value of your couple is a counterclockwise rotation, you can call this the couple on 1 by 2. And then, dang it. Free body diagram of member 2. Take a chunk of the wall. That's equal to the force on 2 by 1, which is equal to the negative force on 1 by 2. And also a couple M on 2 by 1, which is equal to negative M 1, 2. Okay, so this is a lot of stuff to remember if you choose to do it that way, and you can. You can always just Google stuff. But I think a more effective way to think about these joints is to understand how those loads are developed. So where do these loads come from? And especially in 3 dimensions, I think this becomes even more important. Each translation that's disallowed between bodies is caused by a force component in that direction. And each rotation that's disallowed between bodies is caused by a couple between bodies. Each rotation that's disallowed between bodies is caused by a couple. Okay, so let's go back through some of these joints and just try to make sense out of where those loads come from. So, yep, sure.
So on the couple, I can use vector notation for the M.
When you're using, it's because this is a 2-dimensional problem, and so the moment itself is a vector, but you can talk about it in terms of, I guess I have it drawn, this way of drawing it says that the axis can only be in the z direction. You know what I mean? It's, yeah, since this is a 2D problem, rotations can only happen about a z axis. And so in 2D, there's not really any point of treating that as a vector. In 3D, we are going to have to treat them as vectors, and the way you represent components of couple vectors is with this like double arrow notation. So this is how you would represent a couple vector, and then you would write, M vector. But in 2D, we're just talking about a single component, a z component. Okay?
So what is translation? Linear motion?
Yes, that's right. Okay, so let's go back through these and think about this. Let's just do one from each category. So first in the category, that first category where it introduces a single variable and the joint applies a force in a known direction, let's think about what motion is disallowed at the point of contact. Okay, so think about the motion, I guess picture member 2 being fixed and think about the motions that are allowed by member 1. Okay. Can member 1 rotate, first of all? If this is the only thing restricting. Yeah, member 1 can rotate, so we know that there's no couple between them. Okay? There'd only be a couple if its rotation was fixed. Can it translate perpendicular to the surface? No, and that's where we get this force vector. Can it translate parallel to the surface? Yes, and that's why we don't have any other force component besides that perpendicular one. Any questions about that? So now let's go to like a ball and socket joint. Imagine member 2 is like fixed to the ground. So I just think it's easier to imagine what's going on if you do that. So this stays exactly fixed. It doesn't translate or rotate at all. What can member 1 do relative to this? Can it rotate relative to member 2? If that's a hinge? Yeah, it can rotate. So we know there can't be any couple applied by that joint. Can it translate in the x direction? No. Can it translate in the y direction? No. And so we know we have to have 2 force components and no couple. And then go to the last category, the fixed joint. So imagine this part's fixed. With this, imagine these welded together. Can this rotate? No, so there has to be a couple. Can it translate in the x direction? No, so there has to be an x component of the force. Can it translate in the y direction? No, so you have a full force vector and a couple. So that's where those loads come from. Yep. Yeah.
So the only way that we can think of the pin joint is as a socket. Is that the case? Because like if you think about like a pin between 2 plates,
Mm-hmm.
then that can't rotate on like one axis, right? It can't rotate from A to B.
Well, you're right. So you're talking about like off-axis rotations. Yeah, so right now we're only thinking about stuff in 2D. Pretty soon we're going to think about it in 3D, and then that's exactly right. A pin joint like this doesn't allow them to, if you try to push one into the page and pull one out of the page, it does resist that kind of rotation between the bodies. And so this pin joint actually would apply couples. They're just not in 2 dimensions. Or we're not thinking about that in a 2-dimensional problem. But yeah, you're right. Okay, any other questions? All right, let's take a 10-minute break, come back at 5 after 2. We'll start doing some problems.